In this video, we're going to continue to talk about finding the probability of multiple events. Just remember, when you're doing multiple things, this, and this, and this, and then this, you multiply. But you got to always consider, are the events independent? I mean, does the outcome of one event affect the next event? There's really no formula here. You just kind of have to use your brain and walk through it. So here's the first really good example that shows using that brain. So 20 marbles are in a bag, 7 blue, 10 green, 3 red. You reach in and select 2 marbles. Now the fact that I'm getting 2 marbles means that I am not replacing them because I want to get 2 different marbles at the end. So if I put one back, then at the end I'm only going to end up with 1 marble. So I want 2 different marbles, so I am doing this without replacement. All right, what's the probability that both marbles are blue? I get 2 blue marbles. So you just got to walk through it. What's the probability the first time I reach in, I get a blue marble? Well, there are 7 marbles that are blue. They're going to make me happy out of 20 total marbles in the bag. There you go. But now I need it to happen again, a multiple time, a multiple reach into that bag. So I'm going to multiply. But now I got to realize that I took a marble out of the bag. So there's now only 19 marbles left in the bag. And I also assume I took a blue one out that first time. So I needed to get a blue one. So there's only 6 blue left. So then multiply these probabilities together. We're just going to do 7 divided by 20 times 6 divided by 19. Pretty simple. We get 0.111. Or there's 11.1% chance of getting 2 blue marbles. Again, very likely. That is not weird. That's not significant at all. All right, this next one's going to be a little bit different, but some of the same characteristics. What is the probability that you reach in and you pull out a blue and a red marble? So again, at the end, I want to get a blue marble and a red marble. So I'm not replacing. I'm going to select a marble, keep it, select another marble, and at the end, I want them both to be blue. Excuse me, I'm so sorry. I want one to be blue and one to be red. So again, the problem though is that this can happen 2 ways, right? The first marble could be the blue one, and then the second one could be the red. That would work. Or I can have the first one be red and the second one be blue. Again, these are 2 distinguishably different outcomes. I didn't have to do this on the first question because the first question was blue, blue. Blue, blue is blue, blue. You can't make that different. But a blue than a red would be distinguishably different outcome than a red than a blue. But both of them are going to make me happy because both situations end with me having a blue and a red marble. So now we just got to walk through the probability here. Getting a blue on the first marble would be 7 out of 20. 7 blue out of 20 total. 19 left though, because remember I kept that first marble. And of the 19 that are left, 3 that are red. So I can multiply to get that probability. Or let me go ahead and figure out the next one here. Red first, 3 out of the 20 are going to make me happy because they're red. Now there's only 19 left, and I need that second one to be blue, 7 are blue. Now what you notice here is that both of these mathematically are the same. They both have a 7 times 3 in the numerator and a 20 times 19 in the denominator. So mathematically, these 2 probabilities are the same. So you could calculate it twice and add them together, or you could really just calculate it once and then times it by 2 because there's 2 different ways it can happen, and those 2 different ways are equivalent. So 7 out of 3, not 7 out of 3, sorry, 7 out of 20 times 9, boy, I can't talk, times 3 out of 19, and then double that, times it by 2 again, or just do the math twice and add together, it doesn't really matter, but we get 0.111. Now, if you're looking for another way to understand this, some kids like to think about a 2-way table when they say, okay, the first marble could be blue. Not a 2-way table, man. I'm just all over it today. I'm very sorry. Having a hard time talking today. All right, let me explain this again. A tree diagram. A tree diagram helps a lot of kids sometimes see this. So if the math that I just showed didn't help you, a tree diagram may. So you said the first marble could be blue, red, or green. 7 out of 20 that it's blue, 3 out of 20 that it's red, 10 out of 20 that it's green. Okay, then we go for the second marble. Second marble could be blue, red, green, blue, red, green, and then again blue, red, green. Now you got to follow through the probabilities, right? Okay, so you just got to think. If that first one was blue, now the second one being blue would be 6 out of 19. Second one being red, well, there's still 3 red left, so that'd be 3 out of 19. Or green, 10 out of 19, so there's still 10 green left. Now, if the first one's red, there are still 7 out of 19 that are blue, 2 out of 19 that are green, that are red, and then green would still be 10 out of 19. If the first one's green, there's 7 out of 19 that are blue, 3 out of 19 that are red, and if that first one was green, now we got 9 out of 19 that are green. And then you got to say, okay, what branches are going to make me happy? Because remember, I want a blue and a red. So this branch right here will make me happy, get a blue and a red one. This branch right here will make me happy, I get a blue and a red one. All other branches don't end up with a blue and a red marble. So then you just got to track these two branches. Again, this first branch would be 7 out of 20 times 3 out of 19. And this branch right here would be 3 out of 20 times 7 out of 19. And again, those are the same probabilities I just showed you. So sometimes seeing the picture of it sometimes helps kids. Completely up to you. All right, here's a two-way table example. So example we've seen already, 500 total kids. We got freshmen, sophomores, juniors, seniors, kids that wear glasses, kids that don't. And we want, again, find the probability that 2 kids are selected. So again, we're selecting 2 kids. So we want a kid, we're going to pick a kid out, and then we're going to pick another kid out. So not replacement here. We want 2 kids when it's done, so we don't put that first one back. What's the probability they're both sophomores? All right, so we say, what's the probability the first kid's a sophomore? Well, there are 90 sophomores to choose from. 90 kids are going to make me happy if they're selected. I don't really care which one out of 500. But then now we need that second kid to also be a sophomore. Well, now there's only 499 kids left to choose from because I kept that first one. And if that first one was a sophomore, then there's now 89 sophomores left for me to choose from. So sophomore, sophomore. I don't have to worry about another scenario because the only scenario is sophomore, sophomore. So again, grab a calculator, 9 out of 500, 90 out of 500 times 89 out of 499, and the probability to be 0.0321. So that's on the lower side. That's below 5%. So at 3.21%, I would say that this is unlikely to occur to get 2 sophomores. You know, you should get some other kids involved, right? I mean, it would be weird. There's a lot of juniors, sophomores, seniors, and freshmen, right? So it'd be weird to get 2 sophomores. But I wouldn't be shocked if this happened. Remember, I don't really say, oh my God, until we get under 1%. All right, let's take a look at another one here. 2 cards are selected without replacement from a standard deck of 52 cards. What's the probability that both cards are red? So again, we just got to think here. It does say without replacement. So we do want 2 different cards. And we want the first one to be red and the second one to be red. So all right, you think about a standard deck of cards. There are 26 out of 52 cards that are red. And as long as I get one of those 26 out of 52 cards, I'm happy for that first card. But now I need a red one again. Well, there's only 51 cards left in the deck, 25 of which are red, because I already got a red one the first time. So again, I'm thinking conditionally here. What happened on that second red is because of what happened on the first. Very simple. 26 out of 52 times 25 out of 51. Do the math, 0.245. So again, that would be very likely. It would not be weird to get 2 reds in a row. All right, next one here. What is the probability that 1 card is red and 1 card is a king? So again, I get 2 cards at the end. Draw a little pick. 2 cards, and I just need 1 to be red and 1 to be king. What if I have a red card and a king? Well, that's fine. I just, at the end, I need a card to be red. I need a card to be king. So this one, I mean, I could walk through it and do the math, but this one is where a tree diagram, I think, is like really beneficial. So let's start with the king. I could get the king of spades or the king of clubs. Now, those are both black. So I'm going to do king of spade. That's a club there. And the king of spades. Basically, a black king could be selected. Now, the probability of a black king being selected is 2 out of 52 because 2 cards are black kings, right? Now, the other thing that can happen is I could get a red king. That's the red king diamonds or the red king of hearts. And again, there are 2 out of 52 of those as well. All right, but then I'm going to pick another card, right? And that next card, all I really care about is that it's red or black. Now, this is where we have to think, right? If that first card is one of the kings, one of the black kings, then that means that of the 51 remaining cards, because again, I picked 1 card, so 51 cards remaining, 26 are still red. 26 are still red. Now here, of the 51 cards remaining, I already got a black king, so that means there's 1 less black card, so there's only 25 black cards left. All right, down here, if one of those red kings is found, then again, the next card could be red or black. And let's see here. The red card, well, again, if I got a red king, then that means there's now 51 cards left because I got 1 card away. So 51 cards left. And of those 51 cards left, only 25 are red. Because again, I got a red king. Whether it was the red king of diamonds or the red king of hearts, either one, there's now only 25 red cards left. and there are 26 black cards still left because I got a red king. So there's still plenty of 26 black cards left out of 51. So now again, remember what branches are going to make me happy. I need a king. I need a card that's king and a card that's red. So this branch right here is going to make me happy because now listen, I got a king and a red and they're both red. But again, I need a king and a red card. That branch leads to a king and a red card. But this branch right here also leads to a king and a red card. Got a red card. It's not one of the kings, but it's a red card. And then I still have a king that's black. But again, that branch is going to make me happy. So now I just got to think of the branches. I got 2 out of 52 for that first branch. That's the black kings. And then 26 out of 51 to get that red card. This branch down here is going to be 2 out of 52 for one of the red kings. And then 25 out of 51 for the next card to be red. So again, now I just got to multiply each of these out. Let's see here, 2 out of 52 times 26 out of 51. And take your time on that math, and that is 1 out of 51. You could leave a decimal, but I like fractions to be exact. If I can, that's 1 out of 51. And this next one, again, 2 out of 52 times 25 out of 51. And that's going to be a much uglier fraction, but it's still a fraction nevertheless. You could leave a decimal, I'd be okay. But 25 out of 1,326. Now again, I got to add these together, right? Because either one of these options is going to make me happy. Either I get the black king with the red card or a red king with the red card. But either way, I still end up with the red card or king. That's all the question asked about. So I'm going to add these previous two answers together. And get a final answer here of 1 out of 26. Final answer is 1 out of 26. So 1 out of 26. If you are looking for decimals, 0.0385. So again, it would be, I wouldn't call this shocking if it happened. It would be a little bit of a lower, but I don't necessarily think it would be, I wouldn't fall over and pass out if I ended up getting a red card and a king. But again, not a two-way tail, I keep saying that. Tree diagram, walking through what happens really allows it to kind of come to life and see it. I really think so. All right, back to our turkey problem, right? Ham for Thanksgiving, 18% of families have ham for Thanksgiving. So in the long run, if we look at many families, 18% of them are going to have ham. 75% have turkey, 11% have both. All right, 2 houses are picked. What's the probability they both have turkey? So again, multiple houses, we're going to multiply. So the first house having turkey, 75%. But now we need the second house to also have turkey, 75%. Bingo. 0.75 for the first times 0.75 for the second, 0.75 squared, 0.5625, 56.25% chance that 2 houses in a row are both having turkey. Now, I don't have to think about a different scenario because turkey, 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 turkey. You can't flip that around and make it look any different. First house turkey, second house turkey, turkey, turkey. But, some kids could argue, but wait a minute. If the first house is turkey, millions of houses out there, right? And the first one's turkey. So when I get to that second house, if you think about it, there's a slightly less chance, very slightly less chance that second house is turkey because that first house has already been selected and cannot be selected again. But we're dealing with millions of households because remember, 75% doesn't come from 10 houses or a bag of 20 houses. It comes from a large number of houses, that are having turkey. So it's totally fine to leave it at 0.75 and 0.75. And listen, I won't argue. Maybe this second one would actually be like 0.7499999999, because if you technically take a house away that had turkey, you have a slightly less chance. But at the end of the day, it's negligible. Like it just doesn't really matter that much that second house is going to drop a little bit. And this is actually a really, really important idea. And it's the truth, right? When you're working with percentages, as long as those percentages are coming from a large amount of data, large amount of households, it's fine to leave it at 0.75, 0.75. But if you're dealing with a small bag of, 20 marbles, you take one out, well, man, the probability is different now. So it really matters in that situation. All right, let's do another one. And this one's great to look at because we truly have 2 different events. In the last problem, we were looking at multiple events, a first house and a second house, but they were both houses. Here, we're looking at 2 different events, but we're still going to multiply. So here, we're flipping a coin and spinning a spinner. The coin has two sides, tails and heads. The spinner has 7 sections, each numbered 1 through 7, and we're going to assume that those 7 sections are equally sized. All right, so what's the probability of getting a tail on the coin and a 4 on the spinner? So again, multiple events multiply. So I need a tail on the coin, that's 1/2, duh. And then I need a 4 on the spinner. Well, one of the 7 sections is a 4. So the probability of me getting a tail and then a 4 on the spinner would be 1/2 for the tail, 1/7 for the 4, and that's 1 out of 14. Get a decimal if you want. How easy is that? Okay, next question. Probability of getting a tail on the coin and an even number on the spinner. Oh, it's simple. Tail on the coin, 1/2. Now, what's the probability of getting an even number on the spinner? Once again, 7 sections on the spinner. There is a 2, a 4, and a 6. That's even. The 1, 3, 5, and 7 are not. So 3 outcomes are going to make me happy because they're even numbers. 2, 4, and 6. So 1/2 for the tail, 3/7 for the even number. 3 out of 14 is my answer. Multiple events, multiply, man. How easy is that? All right. Here we're going to look at another example of non-independent events, but they're really independent. This is going to kind of piggyback with the turkey problem that I was, kind of talking at length about. You're at a factory, and that makes thousands of marbles, all right? Thousands of marbles, thousands of them, maybe millions of them. They say that 24% of all their marbles are blue. You select 2 marbles from the huge batch of marbles. What's the probability that they're both blue? All right, well, we say, all right, what's the probability that the first marble is blue? Well, they say 24% is blue. Remember, that 24% doesn't come from 24 blue out of 100. It comes from 24% of many, 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 many marbles that are blue. So the first one, I need to be blue. Now, the second one, I need to be blue. But again, listen, if you think about it, if you get down to technicalities here, if you take one marble out and you don't put it back, you are changing the probability of what comes next. So technically, there's thousands of marbles. Technically, that next marble being blue has like a slightly less chance because there's one less marble, but there's thousands of them. So one less marble, like big deal. There's still thousands left. But technically one of them there's one less blue marble as well because I took a blue one out. But again, we still keep it at 24% because what we say is that, yeah, maybe that second marble is slightly less likely to be blue, but the difference is negligible. It could be 0.23999999. Listen, I really want you to just process that if it was a bag of 20 marbles and you take one away, yeah, that's a big difference between 19 and 20. That's a noticeable difference. But when you're at the factory with just thousands upon thousands of marbles, you take one away. Listen, I'm not going to lie. Technically, that's different, but it's not a difference that matters. So that's why we keep it 24% for the first, 24% for the second. 24% times 24% is 0.0576. So you got about a 5.76% chance of getting 2 blue marbles. All right, what is the probability that one is blue and one is not blue? Okay, so we can have blue, not blue. That'd be 24% for the blue, and then obviously 76% for the not blue. If 24% are blue, the opposite, 76%, are non-blue. So again, blue, not blue. But we could do a distinguishably different outcome here. We could have the not blue first, and then the blue. So that would be 76% for the not blue, 24% for the blue. Now again, you take a marble away, I'm going to say the same thing again, you technically are making a difference, but there's thousands of them. It doesn't really matter. There might be a small difference, but it's negligible. Now mathematically, both of these are 0.24 times 0.76, but they're both the same, so you could just do it twice, add them together, or just do it once and times it by 2. So 0.3648. You could even do a tree diagram if you want, showing the first one is blue or not blue, and then after that, blue or not blue, to see that there are 2 distinctly different outcomes, blue, then not blue, or not blue, and then blue. But this whole idea of what I'm talking about here, this idea that there's thousands of marbles, take one away, technically it matters, but realistically it doesn't. We actually have an idea of this. This is actually called the 10% rule. And don't worry a ton about this right now. It's a little bit confusing, but in the future, we need to keep focusing on it. The idea is this. Anytime we select without replacement, the amount n that you are selecting out of the population, capital N, is less than or equal to 10% of that population, the independence can be assumed. Now, a lot of kids are like, hold on, what? Here's the idea. If you have thousands and thousands and thousands of marbles, and you take, even if you take 10 away, yes, you are changing the probability of what happens next because there's 10 less marbles and maybe they're all blue, there's 10 less blue, or maybe 5 are blue and 5 are red, there's less blue, less red. But the idea is that there are so many marbles still left that yes, you are technically changing the probability, but it's what we call it's negligible. It's not that much of a change that it matters. But the rule is this: as long as the amount you take out is under 10% of the total population, it's fine. So again, N is the number we are taking out, and then this is 10% of your population. 0.1 is the 10% of N. Capital N is your total population. So the point is, as long as you take out less than 10% of your entire population, you're fine to assume independence, even if there's not. So this is what allows us for the turkey to do 0.75 times 0.75. Even though that second 0.75 might not technically be 0.75, the idea is if you take 2 houses out of millions of households, you're not really doing anything major. You're not really impacting the probability of what comes next. Technically, maybe down to the 18,000th decimal you are, but it's not that big of a deal. So again, in reality, they might not be independent, but as long as we can assume that the number we took out is less than 10% of the population, it's okay. All right, so let's actually see this 10% rule coming to life. All right, 13% of people are left-handed. What does that mean? It means in the long run, after looking at many people, 13% chance that a random person is left-handed. Many people. There's not a set amount. It's not like we're looking at 100 people or a bag of 10 people or a bag of 20. All right, I'm going to take 4 people out. Now listen, there are billions of people in this world. If I take 4 people out, even if I just did Ohio, let's just do Ohio. 13 million people in Ohio. If you take 4 out at random, yes, technically you're changing the probability because there's now 4 less people. And if all 4 of them are left-handed, then there's 4 less left-handed people. But it doesn't matter because there's so many millions left that you're not making a big enough dent in the probability for us to worry about it. So the point is, if 13% is left-handed, we can assume independence. We can assume that the next person still has a 13% chance. The next person after that still has a 13%. It's not going to go up and down. All right. What's the probability that all 4 people are left-handed? So that means we would need 13% to happen 4 straight times. First person left-handed, second left-handed, third left-handed, fourth left-handed, 0.13 to the 4th, right? Very simple. Left-handed, 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 left-handed. L. No other way that can happen. 0.13 raised to the 4th is, make sure when you're looking on your calculator correctly here, you're moving the decimal. It's 0.0002806. So it'd be very unlikely. That is 0.0286%. That is very unlikely. I'd be shocked if you randomly grabbed 4 people and they were all left-handed. Boy, I'd question that. That's crazy. All right, what's the probability they're all not left-handed? So I need a right-handed. So not left. If 13% is the chance of left, then that means 87% is the chance they are not left-handed, right? I mean, it's just opposites. 13% are left-handed, the opposite, 87%, not. And we need all 4 of them to not be left-handed. So 0.87 to the 4th is 0.573. This is actually very likely. It would be very normal. If I got 4 people in a row that were all right-handed, completely random, that would not be weird at all. All right, 1 is left-handed. This is where we got to open up our minds and think. Now, this could happen a couple different ways. See, all left-handed, that can only happen one way. Left. We need 1 to be left-handed. So that could be the first one left-handed, then not. The second one is our lefty. So first not, second lefty, not. Or first one not, second one not, third one lefty, fourth one not. And then finally, not, lefty. Now, only one of these can happen at the same time, so we're going to add these probabilities together, but they are distinguishably different. Now, here's the good news. If you think about this is where you got to use your brain. All 4 of these are going to look the same. All 4 of these have a left-handed person, 13% chance of that. All 4 of these situations have 3 not left-handed. So that they have 0.87 to the third. Now again, order of multiplication doesn't matter. So it doesn't matter where the 0.3 is. You have 3 0.87s and 1.83. You're going to multiply them together. All three of these mathematically are equivalent, but there are, all four of them, but there are four distinctly different situations where you could have one lefty, 0.13, three nons, 0.87. So I'm going to times this result by 4 for the fact that there are 1, 2, 3, 4 distinctly different situations for this to happen. So 0.13 times 0.87 raised to the third, get an answer, times it by 4. The final answer is 0.342. Again, you got to think about order matters here. It's distinguishably different. Whereas lefty, 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 only one way that can happen. But when you're talking about one left-handed person, you got to think about first that there are 4 ways it could happen. Mathematically, they're all equivalent. That's the good news, but you got to understand it. And again, that 10% rule, again, you don't have to address the fact that you're using the 10% rule here, but you just have to understand that if I'm going to multiply 0.13, 0.13, 0.13, I have to assume that the probability of getting a left-handed person is not going up or down. And that's okay, even if maybe it's truly not when you want to get down and technical to it. All right, hopefully that makes sense, and hopefully this video really helps you out. There's going to be another video with a couple more problems on it if you need it, but I think this one will help you guys a lot.